Good afternoon to all.
Sir.
Good afternoon. Shall we start or you can wait up to 5 minutes or 10 minutes? Okay, shall we start?
Okay.
Right, okay, thank you. So today we're having one more class to discuss about what are the problems for your mid examination, or suppose those who are writing gate examination in 2021, it is very useful to solve the problems in your mid examination as well as for gate examination. Okay, so first we are talking about fatigue loading condition. Okay, I think all of you know. So this is third time I'm going to revise this unit. Why? Because of it is very important for your examination purpose. Okay, na. So one more thing I'm going to share all of you. So majorly in our third unit, the model number 1 problems are coming from 3 theorems, which are in a combined load or combined variable loads. That is called as Soderberg method, Gerber method, Goodman's line method. Okay, na. Second model number 2 is by using these 3 theorems, how we are going to calculate the reversal loading condition. Maybe it is the reversal bending condition, reversal shear condition, and shear reversed axial loading condition. So how we are going to calculate by consider a surface factor, size factor, next what are called as stress concentration factor, and one more thing is endurance limit factor. Okay, now so by considering these 3 to 4 parameters, how we find out the diameter of the bar or thickness of the plate or factor of safety in our second model. Okay, now third model very important in your examination purpose, that is called how to calculate the life of the component. Okay, now how to calculate the life of component by using a SN curve graph, stress to number of cycle graph. Why I am going to attempt one more class in today means, it is very easy, but you peoples are not to understand so many numbers. They're calling us, sir, I'm not having that much of easy to calculate the problems. Once again you just explain the process like that. Okay, that's why I'm going to conduct one more class in only for the unit number 2, that is model number 1, 2, 3 problems. Okay, na? Right. Yes, you can start. So first, fatigue loading condition. I think all of you know what is a fatigue loading condition. That is the ability of the material to resist the load which is in a repetitive condition. That is the constant, the specimen is constant, but you're going to suppose to apply the load is in a repeated manner. That is with respect to time, each and every cycle, we keep on applying a loads in repeatedly. Okay, na. So if the load is constant, static condition. If the load is going to variable or any machine component is going to having a moving condition, this is called as a dynamic condition. But here in our design of mission members, we will completely discuss about fatigue loading or varying load or any cyclic load. Okay, na. These both are having a same meaning, but the fatigue means what? With respect to time period, we are keep on varying the load or keep on applying a load or keep on repeatedly applying a load on a mating component. For example, it is a shaft or gear or any clutch plate or any moving component. So your main duty is, your main aim is, we have to resist the failure when you apply the load in a repetitive manner. That is meaning of fatigue loading condition. All of you remember. But here, when you apply the repeated loading condition, what are the failures will be happen? Okay, now what are the failures? How we are going to overcome the failures? That is very important. Okay, right. Next is, so generally we have to observe these failure, these variable stresses in many more applications like ball bearings, springs, gears, rods, and shafts. Okay, now in this 5 to 6 application, mainly we observe the variable stresses due to the phenomena of only for the fluctuating or fatigue loading condition. Okay, now for example, you will see the spring. When you apply the load, what happens? The spring is going to have to compression. If you remove the load, what happens? The spring is going to elongate. Okay, na? So while you are elongating or compressing, what happens? The spring coil is going to have wear and tear, or crack developed due to fatigue failure. Okay, na? The spring wire or coil diameter is generally failure when you apply the compressive or remove the loading condition in any suspension system. What happened? That the spring coil is going to have wear and tear. In this wear and tear, to form a crack failure under the fatigue failure condition. In ball bearings also, if you're going to use any journal bearing, any roller bearing, what happened? So when the bearing is going to revolving inside the bearing, inside the shaft is going to revolving inside the bearing, what happened? The relative motion will supply it from the shaft to bearing. If keep on supplying the amount of load, amount of motion from the bearing shaft to the bearing, what happened? The bearing cells or the inner surface of the bearing is going to have a fatigue or any crack is going to propagation. So these are all coming only at the repeated loading condition. The load keep on going to change, but in our output condition, we transmit the more amount of power or motion from the one shaft to other shaft. Definitely we have to increase the more amount of load. When you increase the more amount of load, what happened? That mating component is going to have a failure condition. Generally, if they will ask any 2 marks or 4 marks in our main examination, definitely they will ask what are the application and why the variable are important in our fatigue loading condition. At the time, just you discuss this 4 to 5 application and draw these 2 diagrams, it is more than enough. Okay, so in our stress strain diagram, so elastic limit is the phase 1, plastic limit is the phase 2. Okay, now up to elastic limit, what we can do, when you apply the load, that bar or any specimen is going to elongation takes place. When you remove the load, what happen? It is again original position. That is called elastic limit. We are not observing any failure or any deformation or any crack propagation or any breaking will not happen in a elastic limit condition. Why? Because of it is vice versa. Apply load, it is expanding takes place. Once if you remove the load, it regains original position. Okay, na? Is a way in the elastic limit. But once it will start the elongation limit and enter into the yield point location or ultimate point location, what happened? That the bar is not supposed to resist the loading condition. Meanwhile, that component is going to have a fracture or any shear failure will be happen. So why I am going to link these 2 points is, so after crossing a ultimate tensile point, we have to observe the failure in a fatigue loading condition. Okay, na? So in elastic loading condition, we are not have to observe any deformation. Please keep in our mind. In our single point cutting tool also, when you remove the amount of material in our mild steel bar, what happened? In elastic limit condition, we are having only for the discontinuous chip. Yes or no? So after crossing the elastic limit, once it is a plastic limit condition, we are having a continuous chip. Why? Because of the tool wear and tear is more. When you increase the tool life, always we have to maintain the continuous chip. So the continuous chip is what? So once it is crossed the elastic limit in plastic loading condition or plastic limit, the tool is going to remove the more amount of material, then only the amount of material can be cut into the workpiece. Same phenomena here, we are going to use the design of mission members. So once that bar, that load will be increased from the elastic limit to the plastic limit condition, what happened? That bar is continuously elongation takes place. So once at any loading point, what happened? It is going to failure. For example, in our UTM mission, universal testing mission. Okay, so in failure occurs in a variable stress condition, maximum in the ultimate after crossing that ultimate tensile loading point. Okay, na? So in that ultimate tensile loading point, we clearly observe the fatigue failure. Okay, na? Fatigue failure, right? It's a very important point for our gate examination, right? So next. So I think all of you know this. What are the different types of cycles we are going to use in a fatigue loading condition? The first one is completely reversed or cyclic stresses. Okay, na? That is, so when you applied the load, what happened? Initially, it is a minimum stress value. Once if you increase the load, what happened? The stress also increase. Okay now, so here the same point we have to observe the maximum value and the minimum value. That is, the stress always vary from the one value of compression to the same value of tensile. Why? Because of in initial point we are not supposed to get more amount of expansion takes place. Okay now, initially it is a only small elongation. After applying a load, what happened? It should be more propagation or more expansion takes place. That is cyclic stress. Once you remove the load, what happened? It again initial condition. After applying load, it should be expansion takes place. That is, one is the maximum value, one is the minimum value. The same point we have to observe both compressive and the tensile. Those type of stresses we call it as cyclic stresses. These cyclic, the best example is spring. Okay na? So spring is one of the best example. We clearly observe while you're applying load, the coils are going to compression takes place. Once we remove the load, what happened? It is going to elongate. Same single point. Okay na? Single specimen. We observe compressive, that then tensile. Okay na? It is one of the beautiful application. We clearly observe in that cyclic stresses are completely reversed stresses. Okay na? Very important. Next, fluctuating stress. I think fluctuating also, the always the stress will vary from the minimum value to the maximum value. That is, initial itself it is a compressive. Maybe if you're going to assume after applying load it is going to expand, but it is not required original position. Just the value will change from the maximum to minimum. Okay na? For example, when vehicle is going to travel in a high hills area, what happened? The initial, the speed is more. Okay na? So once it will be traveling in a high location, what happened? So whenever the height of the hill is going to increase, definitely we are having a less speed. Like that only, when you apply the small load, small elongation, if you keep on increasing the load, what happened? The specimen will continuously expansion takes place. Those stresses are called as a fluctuating stresses. Okay now, here the value is, or stress value is vary from minimum value to the maximum value. That's clear. So next, third one is repeated stresses. That is, here the stress value is increased from the 0 to the certain maximum. That is 0. Initially we are not having any motion. Okay now, it's 0 only, 0 load or 0 expansion. Once we gradually increase the load, what happened? It will reach the maximum point, like shaft speed or any bearing speed or any clutch speed, any brake speed. In this all application, it is called as a repeated stresses center. Okay na? Next, very important, there is a alternating stresses. Here the alternating stresses are generally we clearly observed in a steering gearbox. Okay na? In our automobile engines, the steering gearbox, here in these two diagrams we clearly observe. Here, see this is a datum point. Okay now, initially it is in a 0 position. Once we increase the speed, what happened? It is going to have a tensile, and also we have to reach that maximum location. Okay, so again the speed level will reduce. What happened? It again reaches to the datum point, that is 0 point. Okay now, from 0 point to the datum point is a variable stress system. Sigma V means a variable stress, sigma maximum is maximum stress value. Okay now, in x-axis time origin, in y-axis expansion ratio, whether it is compression or tension. Okay now, so next one is repeated also, same thing. See here, sigma m means mean stress. In our repeated stresses, the sigma m is always in datum point. Why? Because of the stress value is vary from the minimum to the maximum value of the nature. Okay, that's why here it is called as a repeated value. Okay, just you understand. First one is the, what is called first one, completely reverse or cyclic stresses. Second one is fluctuating stresses. Third one is repeated stresses, and next one is alternating stresses. Okay na? Sometimes they will ask gate also multiple choice questions. Okay na? So on the time it is very useful. We're going to give the answer. Okay, right. So next, how we're going to find out the fatigue fields? I think all of you know. By using a rotating beam mirror beam method, we clearly draw one SN curve diagram. Based on this SN curve diagram values, we clearly calculate the fatigue life or any component life. But how it is? how it is. I think all of you know, right? So see this, it is a motor, is a fixed jaw, is a mobile jaw, load arm, is a load arm, it's a supporting member. Okay na? So once if you start the motor, what happen, it is called as a rotating beam specimen. It is having a high surface finish and also very what you call it as less stress concentration value specimen. Why? Because of if you keep on rotating, we're having any irregularities, what happened, the crack is going to propagate. That's why here highly polished specimen we're inserting between the fixed specimen, fixed jaw and mobile jaw. Okay, once you start the motor, what happened, the beam is going to continuously rotating, which is maximum to minimum speed condition. Okay, once if you hang the loads one by one, first we are going to apply a 10 kilonewton load. Okay na? Then what is the stress? N is first cycle, that is 10 power 3 cycle, first cycle, that is 10 power 0 no load, 10 power 1 we have to apply the load. Okay, what is the stress? 10 power 2, what is the stress value? 10 power 3, what is stress value? So keep on, we are applying a load in each and every cycle. What is stress value? After getting a values from this experiment, we have to draw the graph between the stress to number of cycle In that we clearly observe low cycle fatigue, high cycle fatigue. The low cycle fatigue, the value is range from 10 power 3 to 10 power 6. In the 10 power 3 and 10 power 6, we are not supposed to have any fracture or any what are called as failure will happen while you are applying a load from 10 power 3 cycle to 10 power 6. That is a low cycle fatigue. Okay na? Then once it's crossed the 10 power 6, entire 10 power 6 to 10 power 9 up to n, it is called as a high cycle fatigue. In that high cycle fatigue, we clearly observe the failure of the specimen. I think all of understand. Okay, so in this SN curve is mainly developed by using a rotating beam method. Okay na? In this beam method, what we are going to explain here, so you will keep on applying a load in each and every cycle with respect to load condition. What is the amount of stress will be induced in a given polishing specimen? Polishing. After getting all the values, we are going to draw the curve, that is SN curve. In that curve, where that line is having a straight nature or any bending nature. If the line is constant, what happened? We are not having any failure. So 10 power 3 to 10 power 6 cycle, we are not observing any crack formation or any failure will be happen. Once it will be start the fail 10 power 6 above, it is going to start the failure. Okay na? So this entire information we got after getting a SN curve diagram based on this rotating mirror beam method. I think all of you know. Okay na? But once again I clearly explained, right? So one more very important point is this endurance limit. Endurance limit, what? I think all of you know. Anybody can explain the endurance limit? What is? Can you define the endurance limit? Anybody, can you define the endurance limit? Anybody? Anybody, can you define the endurance limit? Anybody, please? What is meant by endurance limit? No one. Yes, please. Anybody, can you define endurance limit? What is the main use of endurance limit in our design of fatigue loading condition? The ability of the material to resist the load below the yield point stress. Below the yield point stress. Those failures are called as a fatigue. But endurance limit, what? Below ultimate point location. That is the ability of the material which is subjected to repeated stresses value below the ultimate stress point or below the ultimate point value. That is called as endurance limit value. Okay, na? Endurance limit value we have to clearly observe only for the crack formation or whether that specimen is going to start the failure or not. But in fatigue failure, same load if you're going to apply it constantly, no failures. Okay, once if you start the load in a repeated condition, once again or same or variable load condition, definitely it is going to have to failure. Endurance limit is to resist the failure or the ability of the material which is subjected to repeated stresses below the ultimate point is called as endurance limit, or below the yield point it is called as a fatigue failure. Okay, now there is a difference. But these endurance limit and fatigue failures are mainly affected by the size of the component. It's very important. I think all of you know stress is equal to load by area. If you're having a more stress, less area. That's it. So when you take the more amount of more diameter or more length breadth of the component, meanwhile we have to get a less amount of S value. So here the fatigue material which is influenced by only by the size of the component and in which direction we are going to apply the load, whether it is a along the axis or any transverse loads or any perpendicular loads or any inclined loads, that is static nature, or any uh, relative magnitude of the loading condition, or number of load intervals, like how many number of cycles you are going to apply the load. If you are going to take a 400 bar which is having a 40 diameter, so how many number of loads you are going to apply? Okay, now how many number of loads, how many load intervals we're going to supposed to take to consider by applying a in that given specimen. So like that, in this all parameter are majorly influenced to failure the fatigue condition. As a design engineer, we have to clearly analyze what is the size, what is the surface factor, what is the stress concentration factor, what type of load we're going to apply, whether it is static load or dynamic load. Okay, now how many number of flow intervals or how many number of cycles we clearly understand. So then only we have to optimize the failure. Otherwise it is very difficult to consider to design any member in our fatigue loading condition. Okay, right. So next this whole thing I will explain. So next endurance limit, okay, it's completed. Next, so see this. So in our fatigue loading condition, I think all of you know. So once if you calculate the mean stress value, okay, now once if you calculate the mean stress value or variable stress value, we are going to remember some formulas. Okay, now. So in our fatigue loading condition, the ultimate goal is we have to calculate the diameter of the bar or plate thickness or factor of safety. So each and every model, these three parameters we are going to calculate. Okay, if it is model number 1 or model number 2 or model number 3 or any gate examination, just we supposed to they were supposed to ask how to find out the factor of safety or how to find out the diameter of the bar and how to calculate the what are called as this thickness of the plate. Okay, so as a student, you have to first, when you see the question paper or any computer examination question, first the problem is coming which theorem? The given problem is coming under which theorem? Whether it is a Goodman's line method, whether it is a Soderberg method or any Gerber method. First, you have to identify whether the given problem is coming under which type of theorem in our fatigue loading condition. Once if you get that clarified, immediately we have to write the given data. After getting given data, you are going to calculate, first one is the mean stress value. Okay, na? So mean stress value. Okay, here, so the sigma mean, M is sigma mean. The mean stress is equal to, the formula is sigma maximum, that is summation or average of the maximum stress to the minimum stress value. Please, if anybody still are having any doubt, just note down in any one paper. Okay, sigma maximum plus sigma minimum by 2. It's a basic formula you have to remember in your whenever if you're going to solve the problem. So when you calculate the mean value, if it is stress or if it is load value or if it is torque value or if it is bending, whatever it is there. But once if you calculate the mean value, That is summation of the respective term, or it is sigma maximum plus sigma minimum by 2, or if you want to calculate the mean load or WM antam kada, mean load is equal to what it is? It is called as W maximum load plus minimum load by 2. Maximum load plus minimum load by 2. This is a way you just find out what is the mean value of that respective variable. Okay na? So W maximum plus W minimum by 2. So this is the way you just remember the formula. Okay. So next, if you want to calculate the variable stress, okay na? So that is sigma V, that is variable stress, is equal to what it is? It is a summation of two respective loading condition or two respective stress condition. That is sigma maximum minus sigma minimum by 2. Sigma maximum minus sigma minimum by 2. This is a way you just calculate first the mean value and variable value of the respective term. Okay na? Right. So see this. So here one more very important term is called as alternating stress. That is sigma A. We are called as sigma A. So at outside, the sigma A is also called as sigma V. Okay na? Variable stress or alternating stress, both are same. So in our any computer examination, they will ask alternating stress is also called as variable stress. The formula sigma maximum minus sigma minimum by 2. The sigma A or sigma V, both are same term, don't confuse. In some textbooks they will give the sigma V always. In some textbooks they will give sigma A. Okay na? If you go and see that Sadhu Singh textbook, they will call it as sigma A. But in R.S. Kurmi or any what they call it as Bhattacharya, they will call it as sigma V is a variable stress. Okay na? So sigma M means or WM means it is a average of the respective words or respective parameters. Sigma V means differentiation or subtraction between the two respective variables. Like that you just remember in your mind. Okay, right. So next, see this variable or alternate stress, mean stress value. Okay. So next, so these three are very important terms. That is a load concentration factor is the first one, or I told in the last slide. Surface finish factor, and next size factor. Okay. So first, the very important one is how we are going to take the value from the graph. When you calculate the surface roughness value, how we are going to calculate. Okay now, in our main examination, maybe they will give the ultimate stress value. That is, for example, in our given problem, mild steel bar, the sigma U is equal to 320 or 340 megapascal. Okay na? While you are solving of the problem in model number 1 or model number 2, how we are going to take the 1 minute one 20 minutes. Okay, so when you give the ultimate stress value is 340 megapascal. Okay, sigma U is equal to 340 megapascal. So based on the ultimate stress value, just we're going to consider and we're going to calculate what is the surface roughness value. See, all of you, it is very important. Okay, so before going to problem, 1 minute. See this. So first your main aim is, first you calculate the surface factor, that is KF. Okay, surface factor. Next one is size factor, KSZ. Okay, next one is K surface factor, K surface factor. Next one is called as load correction factor, that is K. If it is KB, load correction factor for bending. Okay na? If it is KA, load correction factor for axial loading condition. If it is tau, that is tau, it is a load correction factor for shear. Okay, na? So these three terms are very important, are coming under stress concentration factors. Okay, so next kf means stress concentration factor for notches. For notches, ksz means size factor. K surface finish factor. K surface is called as surface finish factor. This K surface finish factor we are going to take from this graph. Please, all of remember. So sometime they will not give you the given data in your examination. At the time, just you bring the graph to the examination cell. You have to take the value from this graph. Okay. So next, so maybe if suppose they are going to give a 340 megapascal, the type of specimen is a polished one. Okay, na mild steel polished specimen. So see this. Where is 340 megapascal? Ultimate stress level 280, 282. So 340 maybe nearly this point. Okay. So just you draw in x-axis ultimate value, in y-axis surface finish factor. Below the graph, what we called as, we're going to see the number of lines. First line is called as mirror polished one, mission one, sharp circular notch with mill scale, water specimens like salt water. So see all the lines. In our given problem, they will give one small link. Maybe the specimen is a mission one, suppose. So just to draw one straight line to that curve. Where is the mission line? This one is the mission line. Okay, now just to draw one straight line to that graph. What happened? This line is going to touch somewhere in that graph. See this? From this point to just to draw one horizontal line. What happened? This value is 0.9. This 0.9 is the K surface value. I think all of you clarify your doubt how to take the value from graph. All of you clarified? All of you clarified? All of you clarify your doubt. Okay, so this K surface value we are going to take from the graph. Okay, based on the ultimate stress value, you have to take the surface finish factor. Okay, next one is size factor. See this? Size factor generally we have to take from the diameter values. Once again, I will see you. Okay, the size factor generally consider or take from the diameter of the bars. Okay. Okay, so that is a K surface factor. Okay, K size factor. K size factor, the value is coming from only for the diameter. If the diameter value is 0.72, 50 mm. 0.7 to 50 mm, the size factor value is 0.83. Remember all of you, K size factor is equal to 0.83. This constant value. In our problem, they will give the diameter value. Based on the diameter value, you have to take that size factor. Ledu, if the diameter value is 50 to 100, 50 to 100. The K size factor value is 0.87. 0.87. If the diameter value is more than 100 mm, that size factor value is 0.89. 0.89. Okay, these are three values you have to remember while you are solving the problems. Right? There is a K surface value and a K size value. Kf is, I think all of you know, the Kf value you have to take from the notch factor. Notch means that Q is equal to Kf minus 1 by Kt plus 1. Kf minus 1 by Kf minus 1 by Kt minus 1. From this relation, you have to take that Kf value. But before that, just to calculate the Kt value. This Kt value is take from the table based on the type of specimen that I will explain. Okay, now next see this next load correction factor for bending or for axial for shear. Okay, so if it is a reversal bending condition, the Kb value is 1. I think all of you know. For axial loading condition, the Kb value is 0.8. Okay, if it is shear loading condition, 0.55 for ductile material, 0.8 for brittle material. These three values always constant while you calculate the load correction factor. Based on the given problem, you have to take this value. Okay, na? I think up till now, I think all of you know how to take the value K surface factor, K size factor, load correction factor. Any doubts? Babu, any doubts? Ditlo? Are you having any
No,
doubt?
sir.
No. Okay. So why? Because of one. Why I am going to tell these things is these three are very important. If you take any problem, first you just note down all this value. Then only we substitute the given equation. So first is load correction factor for bending is 1. Axial is 0.8 for shear, 0.5 for ductile material, 0.8 for brittle material. Okay, na? So in first you have to calculate the endurance limit. I think all of you know, that is sigma E kavala. So once if you calculate the sigma E value, then only we substitute the correction endurance limit value. So in sigma E, what it is? If it is bending, if it is reversal bending, what happened? It is sigma EB. Sigma E is equal to sigma EB. How it is going to write? Sigma E into KB. I think all of you know sigma E into KB. That is in case of bending load condition, reversal bending load. If it is reversal axial load condition, sigma EA is equal to sigma E into Ka. Sigma E into Ka. Okay. If it is reversed shear load condition, what it is? That is tau E is equal to what it is? Sigma E into Ks. Yes. So these three are coming only for the endurance limit in reversal condition with respect to bending, axial loading condition, shear loading condition. Just you expand the given equation. Okay, na? Sigma EB means sigma E into KB. Sigma EA means sigma E into Ka. Tau E is equal to sigma E into Ks. This KV value, Ka value and Ks value you have to remember in your mind. Then to take the values from the standard values. Kb is equal to 1, K is equal to 0.8, then K5 is, tau is equal to, Ks is equal to 0.55 for ductile material, 0.8 for brittle material. Like that, you first calculate the reversed loading condition in endurance limit value. That's the first part. Okay. The second part is size factor. Second one is size factor. Okay. The size factor, in the size factor also, we are going to calculate the endurance limit in the size factor. That is sigma E1. We generally expressed the term is sigma E1. Okay, na? Sigma E1 in case of reversal bending. Okay, na? That is sigma EB into K size factor. Sigma EB into K size factor. K size factor into K surface factor. K size factor into K surface factor. Okay, now how we are going to write the sigma EA? Same routine. That is sigma E into KB. Sigma E into KB into KSZ. That is size factor into K surface factor. Like that, you just clearly expand each and every case in our three loading condition. If it is axial loading condition, sigma EA into K surfaces into K size. What about sigma EA? Sigma E into Ka. Okay. Next, in shear loading condition, tau e into k surface into k size. How we are going to write? Sigma e into ka into k surface into k size. Like that, we clearly understand. You clearly understand the concept, then only can substitute the values in our problems. Okay, na? The next surface already I told you. Okay, so next correction. This is very, very important. So in this relation is we have to use to calculate the what are called as a correction endurance limit value. Correction endurance limit, that is sigma e is equal to kb into ksz, that is size factor into k surface factor into kr reliability factor, kt value theoretical stress concentration factor. Stress concentration factor is called as a reversed sigma e dash. Reverse sigma e dash. Actually, it is sigma e. This is only SE. Okay, na? SE means sigma e. How to calculate sigma e? Based on the type of loading condition. Okay, na? That I will discuss in problem. Okay, right. So I think what is meant by stress concentration factor? I think all of you know what is meant by stress concentration factor. The ability of the material to abrupt or any irregularities present in the specimen or any abrupt changes in the given specimen is called as a stress concentration factor. Okay, na? The meaning is we are going to observe clearly irregularities or stress distribution entire area or entire specimen, that is called as a stress concentration factor. This stress concentration factor is majorly happen to failure like in a crack or any what are called as the specimen is going to have to shear area. So your main aim is we have to maximum to reduce the stress concentration factor, then only it is very easy to avoid the breakage or any failure of the specimen. But how we are going to avoid? By making a holes or by making a what are called as notches, threads, small holes, fillets, chamfers. So in this methods we have to provide on the specimen, then only to clearly reduce the amount of stress concentration factor. Okay, na? One already I told in the class. Okay, so next very important one is notch sensitivity factor. Why? What is notch sensitivity factor? It is the ratio of actual stress to the nominal stress. Okay, na? Maybe for example is in our mission tools lab we are going to form one strip turning operation. The first length is 40 mm 50 diameter, second length is 20 mm 30 diameter, third one is 10 mm 15 diameter. So here the area is the, the the areas keep on going to changes, but as our design engineer we have to check whether the discontinuous specimen or whenever the area is going to changing that junction, whether it is having a radius or any fluid we are going to provide or not. Okay, na? Why means here the actual stress somewhat is going to increase to the nominal stress. Ekkada? Where that near or where that discontinuous is going to happen in the given component, in that area we're going to clearly calculate the notch value, that is called as notch sensitivity value. That is, it is defined as the degree to which effect of stress concentration is actually reaches, whether it is low stress concentration value or high stress concentration value. Just we have to find out whether it is low means our specimen is safe zone. If you not have to maintain the lowest amount of stress concentration value, it is going to breakage. Okay, na? So it is mainly defined as a ratio of increase the actual stress to the nominal stress value at the junction of the specimen or any discontinuous of the specimen where that area is going to changes. In that point only we clearly calculate the notch sensitivity value. That formula is Q is equal to kf minus 1 by kt minus 1. Q is called as notch index or notch sensitivity factor. Kf is called stress concentration factor. Kt is called as theoretical stress concentration factor. So we have to find out this kt value. How it is? Q value they will give. The kt value you have to calculate based on the specimen. Whether it is a hole with circular plate or any step turning operation in a cylindrical bar So based on the standard table, we have to calculate the KT value. Q value they will give in our problem. Based on these two values, we have to calculate the KF value. Okay, right. Next, see this notch radius R, and this from this graph. Sometimes you're going to calculate the Q value. How it is? So this in this graph they will give the specimen like this. It is a stepped bar. In this stepped bar, we're going to provide one fillet. See this fillet. They will give the fillet radius, and they will give the height of the fillet and radius. Based on these two values, we first calculate the radius value. Based on radius value and type of material, we are going to take the Q value. Maybe in our problem they will give the aluminum. The R value is nearly 4 mm. R value is 4 mm. If they will give the radius value for a stepped specimen, R is equal to 4 mm. The type of material is aluminum. Just you draw one straight line. Where that R is 4, here R is 4. That is the radius is 4 mm. So from this to draw one straight line. Where it is going to touches the graph for aluminum. Here to draw one straight line. Okay, na? So this is called a Q value. So if they will give any radius value from this graph, we have to calculate the Q value. Okay, na? So like that you just find out the notch value. Okay. So next, I think it's all we don't have any necessary. See this. So low cycle fatigue, high cycle fatigue. See this is a low cycle fatigue. Where it is 10 power 0 to 10 power 3. It is low cycle. After 10 power 3 or 10 power 6 maybe, okay na, 10 power 3 is coming under a high cycle fatigue. So here at 10 power 6 only we clearly observe the failure. Okay na, clear observe the failure. So from 10 power 0 we clearly understand the curve is slightly fall down takes place. Why? Because of when loading is increases, what is the amount of resisting power? It is gradually reduces. If keep on reducing the resisting power, what happened? At the final, we are going to have to specimen failure takes place. From this point, we clearly observe constant line. Constant means what? The completely specimen is going to failure takes place. It's clear. There is a main difference between we have to observe in the low cycle fatigue and high cycle fatigue. But as a design engineer, we clearly calculate where that is going to failure. Okay, na? Right. So next one more very important one is combined theorem problems. Okay, combined loads. See this. So here in our fatigue failure, very important factor is what are the theorems should influence it. What are the theorems should influence it while you calculate the fatigue loads. So generally we are going to use two theorems mainly. There is Gerber method, Soderberg method, and one more theorem is called as Gerber method. But in our syllabus, the problems are coming only for the Gerber and Soderberg. Sometimes they will ask anyone derivation, or sometimes we're going to calculate the diameter of the bar based on the three theorems. So whenever they're going telling three theorems, then only we have to use three theorems. Otherwise, maximum number of problems we are going to use only Gerber method, Goodman line method and Soderberg method. Okay, now combine means what? If any two different types of stresses are combining takes place to get a failure in a given specimen, it is called as a combined steady and variable stresses. Okay, now so here combined means it is a maximum stress. Variable means it is a variable stress. Variable means subtraction. Combined means addition. Okay, so by taking place of these theorems, how we are going to calculate? So under combined stress, steady and loading condition, we clearly use three theorems. One is the Goodman's line, Soderberg line, Gerber line. Okay, see this graph, all of you. In x-axis, we're having a 2 points. That is sigma u point and a sigma y point. Sigma u means ultimate stress value. Sigma y means yield point stress value. And a sigma e is endurance stress point. Okay, so when you take the Goodman line method, okay, now this Goodman line method, we're going to plot the graph or line from the ultimate stress point to the yield point stress. That is, we have to form any relation between endurance limit stress and ultimate stress point. That theorem is called as Goodman's line method. This theorem is mainly applicable for brittle material like cast iron, steel, brass, aluminum, like that. Okay, so otherwise, if you're going to draw any graph between the endurance limit and yield point value, that is called as Soderberg line. This method we recommended both ductile and brittle material. One more is called as Gerber method. So the Gerber method and the Goodman's are both are same. The main difference is in Gerber parabola, a parabolic curve drawn between the endurance limit stress and the yield, endurance limit stress and ultimate stress point. That is called as Gerber parabola method. These three theorems majorly used any design field for getting a fatigue failure condition. These three theorems are very important. Okay, now once I tell you, Goodman's line means the theorem is mainly applicable for endurance limit to the ultimate stress point. The Soderberg line is a line is drawn between the endurance limit to the yield point stress, that is called as Soderberg line. A parabolic curve is drawn between endurance limit stress to the ultimate stress point, that is called as Gerber parabola method. I think all of it clear. Okay, so next, combined study. I think all of you know, right? This one is already explained. Okay, so first one is Goodman's line method. Okay, na? So all of you remember this graph. For gate examination also, they will give one 2 marks question for this concept. Very important. In the time, just to remember this graph, it is very easy. All of you see this graph. So here we have to take in x-axis. So first of all, what is Goodman's line method? A line is drawn between the sigma E and sigma U. This is very important. Just you have to remember these two terms. Then only it is easy to remember in our exams. Okay. So the curve, the theorem is mainly explain the relation between sigma E and sigma U. That's why here in our x-axis we're going to take the sigma U by factor of safety is the distance from the point O to point D. Okay. This is the sigma U is the point in the x-axis. Sigma E is the point in y-axis. Okay. In x-axis, one more is the mean stress value. In y-axis, it is a variable stress value. Okay. From this graph, we clearly observe we may have to finally verify two triangles. One is the PQD is the one triangle, and the next what is called as OCD is the second triangle. Okay, na? COD is the one triangle, PQD is the one triangle. The PQD triangle height is sigma V and base is sigma U by factor of safety. Is entire length from the point O to point D. Okay. So same, the triangle COD, the base distance is sigma U by factor of safety and the vertical height is sigma U by factor of safety. Okay, na? According to similar triangle method, we have to take the equation maybe PQ by CO is equal to QD by OD. Okay, na? See this PQ. This PQ by this small triangle height by bigger triangle height. PQ by CO is equal to what are called as OD by OC. OD by OC. How we're going to write OD? OQ minus OD. The same thing you have to write here. OD minus OQ. Just you substitute all the values in this given equation, you have to finally get the formula is 1 by factor of safety is equal to sigma M by sigma U plus sigma V by sigma E. That is, sigma M means mean stress, sigma V means variable stress, sigma U means ultimate stress, and sigma E is endurance limit stress. That's why from starting itself, I am clearly explain how to calculate the mean stress value, how to calculate the variable stress value. I think all of it clear. Okay. One more very important point is you have to remember Goodman's method is what the relation between the sigma E and sigma U. See this here, sigma E and sigma E. Why? Because it is a Goodman's line method. Sigma E for variable stress, sigma U for mean stress. If it is Soderberg, 1 by factor of safety is equal to what is relation? The Soderberg line is mainly applicable for endurance limit and yield point strength. That's why it is sigma m by sigma y plus sigma v by sigma e. These two are always constant. Okay, na? For the sigma mean only, respect to such is going to vary. If it is Soderberg, is sigma y. If it is Gerber, if it is Goodman, sigma u. Like that, you just remember the formula in your mind. Okay, that is the way you just find out the what is the parameter we are supposed to calculate. Okay, so if it is a Goodman line method, 1 by factor of safety is equal to 1 by factor of safety is equal to sigma m by sigma u, sigma m by sigma u plus sigma v by sigma e plus sigma v by sigma v. It's a basic formula. It is a basic formula you have to calculate. If it is Soderberg method, 1 by factor of safety is equal to 1 by factor of safety is equal to what it is? It is sigma m by the Soderberg method, sigma m by sigma y. Y means it is a relation between sigma e and sigma y kabatti we have to use here sigma y plus sigma v by sigma e. This is a basic formula. You have to calculate the factor of safety or any diameter of the bar or any thickness of the specimen we have to calculate. Okay, so next see all of you, same formula here coming. See this. So basic two formulas we clearly use to find out the factor of safety or diameter or whatever it is there. Okay. So next on problem, see here all of you. So in this problem, determine the thickness of a 120 mm wide plate. Okay, they will give one plate that width is 120 mm. We have to find what is the thickness. Okay, and also they will give one more two more factors are maximum load value and a minimum load value. Okay, na? So you have to consider some you have to consider some standard parameters. That is, they will give sigma e value, sigma e value and a sigma y value. So in our problem, they will not mention any theorem. Based on the stress values only, we clearly confirmed it is Goodman's line method or it is Soderberg method. If they will give sigma e value and sigma y value, the theorem is what? Soderberg method. That is the way you just clearly confirmed and use the theorem. If they will give endurance limit stress value and ultimate stress value, the theorem is called as a Goodman's line method. Based on the stresses, we have to calculate the type of theorem. If they will give three values like endurance limit value, yield point value, stress value, and ultimate, so you have to calculate two theorems. In the two theorems, which one is maximum value? Just you take that value. It's clear. But in this problem, they will give only two stress value. One is the sigma e value and sigma y value. That's why here we have to calculate the thickness of the plate based on the Soderberg method. That is the way you just confirm what type of theorem here we have to use. What is the formula? 1 by factor of safety is equal to sigma m by sigma y plus sigma v by sigma e. This is a basic formula. In this formula, already they will give some data. That is sigma y they will give, sigma e they will give. What we duty? What is we work? We have to calculate first sigma m, sigma v. How to calculate sigma m value? How to calculate sigma m value? It is load by area. Yes, sigma m this is equal to load by area. But they will give two loads, W by A. Okay, na? If it is maximum stress value, if it is mean stress value, sigma mean is equal to W mean by area. If it is a variable stress value, a variable load by area. Variable load by area. How we are going to calculate variable load and mean load? Anyone? How to calculate mean load and variable load? How to calculate a mean load? Anyone? Mean load and variable load. The mean load is what? Already they will give one tensile load, one compressive load. Okay, compressive means -1. See, all of you see the problem. Maximum load is 250, minimum is 100. Same. Mean is what? W maximum, that is maximum load plus minimum load by 2. Maximum load plus minimum load by 2. That is called as a mean load concept by 2. If it is variable means maximum load minus minimum load by 2. Maximum load minus minimum load by 2. This is the way you just calculate. What are the values here getting? Just to substitute here. See. Okay. Here also same thing. First you calculate the mean load value. That is maximum plus minimum by 2. S. Next sigma m. Just to calculate the stress value. Sigma m is equal to W mean by area. Area means what? The plate is circular, not circular one. It is a rectangular one. What is area? With thickness. So 120 into T. What your final requirement? Thickness. But here they will not mention in thickness value. Just they will give only width value. That's why it is a B into T. What is the B value? 120. So finally you have to get the mean stress value in terms of thickness. Same in variable load also. WV is equal to W maximum minus W minimum by 2. Sorry, minimum by 2 here. Okay. So that is 75. Then variable stress is variable load by area. Variable load is already we find out 75 by 120 into T. So these two values we have to substitute given equation. Finally, you will get the thickness value. Okay, na? Simple logic only. The thing is, first you identify the theorem. What theorem here we are going to use? Whether it is a Soderberg line or any Gerber method or any Goodman's line method. So based on the theorem only, we have to get the final answer. Okay, I think all of you understand how we are going to use these theorems and how we are going to solve the problems. This problem same thing. Here also same thing. Okay. So next one more is they will give the sigma E value and sigma Y value. The theorem also coming under Soderberg method. And one more they will give the minimum load value and maximum load value. Okay, na stress concentration factor. That is, they will give the KF. They will give KF 1.8. Factor of safety is 2.0. Here we calculate the diameter of the bar. It is simple one. Okay, na? So always you just remember, if they will not mention any surface factor, any size factor, it is model number 1. If they will mention take size factor, surface factor values, it is model number 2. Okay, na? On the time I am going to explain how to solve the problem. It is clear up till now? Any doubts? Any doubts up to this?
Nothing, sir.
Remaining students, if you have any doubt, just you ask. If you have any doubt, just you ask. If you have any doubt, just we ask. Okay, one more thing I will explain. Just you all of you wait. Okay, my screen is visible to all of you? It is visible to all of you?
Yes, sir.
Yes. So in this, we go for a second model. Okay, it's very important. In mid examination also, I will give one question. Okay. So see this. Yes. These type of problems are very important for our main examination. So model number 1 very easy. I think all of you solve. Model number 2 is somewhat difficult. Okay. See all of you. These two are okay. This one okay. So next. Yes, this one. So generally they will give problem like this. Okay, na? So in our problem, if they mention any notch value or any notch sensitive value or any size factor value, okay, na? This problem is coming under model number 2, first of all. Okay, na? So next, second thing is, if they will mention any beam, or a type of beam like cantilever beam or a simply supported beam? Yes. Okay. So here these problems, first you note down the given data very carefully. What they have to give? Ultimate stress sigma u they will give, yield point they will give, and maximum load value, minimum load value, q value, and k size value. Okay na? So find out the first you find out what are the necessity or what are the important variables we're going to substitute the given equation. That is k surface value, next k size value. These two are very important. You have to calculate. If these two values are already given, no need to calculate. But here in our problem only they will give the size factor. They will not give any surface factor. How we are going to take these surface value? We have to take from the ultimate stress graph. Already I told in last slide. No. So from that graph, we clearly find out what is the surface finish factor. The type of one is steel, mission 1. It is a mission 1. So in x-axis, it is ultimate value. In y-axis, surface finish factor. Based on this type of material, we are going to take the k surface value. Already they will give the k size factor. Okay. So once if you get the clarification, immediately we have to find out how to calculate the stresses value. Any theorem, you have to calculate mean stress value and variable stress value. Mean stress value, variable stress value. Okay na? So, but here they will give load value. But the type of beam is cantilever. How can we calculate? Okay na? At the time, based on the maximum bending moment, value for cantilever beam or simply supported beam, we find out the stress value. Okay na? That is what is the maximum bending moment for cantilever beam? It is load into length, W into load. But here they will give maximum load value, minimum load value. That is maximum load into length value, minimum load into length value. See this, all of you. See. So first what is maximum bending moment is equal to what is maximum load into length. Okay. So next, what is the minimum bending moment? Minimum load into length. Why? Because it is a cantilever beam. But your main duty is you calculate what is the maximum stress and what is the minimum stress. According to maximum shear stress, maximum bending moment formula, M by I is equal to E by R is equal to sigma Y. From this relation, you have to calculate the bending stress in maximum, bending stress in minimum. Okay na? That is sigma B, B into Y by I. Okay na? MB means maximum bending moment, Y means distance from the neutral axis. Y is equal to D by 2, depth by 2. I is equal to BDQ by 12. Why? Because of it is a cantilever beam in rectangular position. BDQ by 12. Okay. So these entire values we have to substitute and you can get the sigma B maximum value. Next, what is the minimum load value? Same. Minimum bending moment into Y by I. That is minimum bending moment value into distance value by moment of inertia. Okay na? So these values we are going to substitute in the mean stress value and variable stress value. We have to get the value in terms of diameter. That means what I am telling is here, whenever they clearly mention the cantilever beam, you have to calculate the maximum bending moment or minimum bending moment equation. Okay na? So otherwise it is very difficult. Once if we get all the values, so to substitute the given equation or given theorems, we have to get the answer. But here they will give the pre-values. They will give only endurance limit. They will not give any endurance limit value. They will give only for the sigma U and sigma Y. But you calculate the sigma E value. The sigma E is what? For steel. Here in problem they will give steel. For steel, what is the sigma E? Sigma E is equal to 0.5 times of sigma U. All I told. Sigma E is equal to 0.5 times of sigma U. Sigma U is the relation. From this relation, you calculate the endurance limit value. That's why by using these two theorems, you calculate what is the diameter of the bar. Okay na? So it is a very important problem in our main examination. So if any doubt, still if you any doubt, tomorrow or after tomorrow will come exam, no. So just once you ask the doubts. Okay. So this all I think already explained. See this. It is very important problem. See all of you. See same problems, same cantilever beam or cement supported beam. Okay, na? So any doubts till now? Any doubt till now?
No, sir.
Okay, my time is 4:05. Okay, I'm stopped here. If any doubt, just we ask. Otherwise, we have to close the session. Okay. Any doubts for mid day